my name's Lauren, and I'm a fourth-year PhD student in Todd Murphy's lab.
And I'm Camaraya, and I'm an undergraduate student also working in Todd Murphy's lab. Today we're going to look at a physical example of diffusion, and then we're going to use computational software like MATLAB to actually analyze the results that we get.
So we have a couple of equations here that you're going to need to use in order to do the analysis that we're going to talk about. So the top one is something you've seen before from lecture, so just your standard equation for diffusion as a function of x. But what you're going to need to use for this experiment is actually a function of x and t. So now we're looking at diffusion both in space and in time.
So we're going to actually do the experiment today with water as our base fluid. And all we're going to do is drop this food coloring dye into this bowl. And Lauren is going to take photos as this dye diffuses in the water.
So you can use any old camera. I'm just using a phone camera. And I'm going to start taking pictures as soon as she drops the food dye into the water, and then take a picture about once a second.
So you can see the dye diffusing in the water. If we let time go to infinity, the concentration at every point would become equal and it would be uniformly distributed. So I'm going to show you a couple images now that we took basically on a smartphone or on your computer webcam. And this first image is right when we dropped the dye in the water. And you can see that we cropped out so that we can see just basically a 1D image of diffusion. And this is because the analysis is a little bit easier using the equations that you guys already have available to you. But in the bowl, we're obviously seeing 2D diffusion. The second image that I'm showing you right now is after a couple seconds of diffusion occurring. And then here's a sample of the MATLAB code that you will be using if you use MATLAB. And this is using kind of these cool functions that are built into MATLAB with the license that you guys have available to you. If you use Python, some of these will still work, but we've also given you instructions to help you write the code that you will need to be able to do this experiment. And then this final image is kind of what you're solving for, which is finding this coefficient, this D constant that varies with the fluids that you use.
So what we see here is that even using these really simple materials that you might have around your house already, and a couple of pretty simple equations and a couple of lines of code, we're actually able to estimate something that's actually meaningful about these materials. So I'm going to talk about how the basic ideas that we talked about in terms of the diffusion experiment apply to research that I do in Todd Murphy's lab in terms of search for mobile robots. So we just saw that when you add a drop of dye to a tank of water, what happens is that as time elapses, you move from a very concentrated area of dye, so something like a delta function, to a distribution that's now much more uniform. So the concentration of the dye is equal everywhere in your container of water. And what you'll see if you do the experiment is that by taking measurements, you're able to estimate something about the system that you're working with, so some property of the fluids. And so what I look at when I'm thinking about search and estimation in mobile robots is how do I take the best measurements to estimate some property of the environment. So for example, in search, you want to localize an object. So to put this into context a little bit, I want to think about an example. So if you think about using a metal detector, so if you're on a beach, you have a sensor that you're moving around, which is going to beep if you come in contact with metal. So if you're trying to find some money or some change in the beach, you get to move this sensor around in order to find change. And when you're talking about search, typically you assume that you don't know where something is from the get-go, so you're trying to search for something. So another way of saying that is that your belief is totally diffuse. So we assume that now we have, instead of a container of water, we have maybe a sandbox that we're searching in. And so our belief, so our understanding of where some change is likely to be is completely diffuse over this area. So we know that there's some change in this particular area, but within that, it's equally likely that this money that we're looking for is located at any point. And so our goal during search is to use our sensors and to collect measurements so that now instead of having a diffuse belief of where some object or some change is located, we want a concentrated belief. So we want to go from this very diffuse understanding to a very concentrated understanding. So in this way, our objective for search, if you think about it in terms of our understanding and our belief of where an object is actually quite a bit like reverse diffusion. So I'm going to talk a little bit about some research that we're actually actively doing in our lab. So this is using a robot that is inspired by a biological fish. So this fish moves around and it senses voltage perturbations in water. So if it's trying to localize some object, it's going to measure a different voltage signal if it's close to that object as opposed to further away. So this is how it's sensing anything about its environment. But in an example like this, and also with the metal detector, you have to move your sensor around in order to actually get any measurements or to obtain any information. So in the experiment that you're going to do, you get to take a picture. And because you're taking an overhead picture, you're measuring all of these pixels at the same time. So you get a measurement in every space of whatever your tank or your sandbox is. Typically, so for this fish example or for a metal detector, you don't get to do that. The metal detector, the range of the sensor is really small. Maybe it's heavy to carry around, and it's going to take a lot of time and a lot of energy. So you want to be able to plan movements that are efficient. So you want to take the best measurements you possibly can. And that's the basic idea of what I'm trying to do in my research, is to try and select movements that are going to give you the best measurements to drive this reverse diffusion of your understanding of where some object is as quickly as possible. So I can show this path that the robot's going to take. So this is a simulation of an actual path the robot would take moving around a tank. So it looks kind of random, maybe a little bit unintuitive. But what we see is if we actually look at now the distribution of our belief, it goes from something very diffuse. So this is looping. It's essentially uniform in the beginning, and as the robot moves around and as it collects more measurements, we end up with something that's very concentrated, and that looks quite a bit like what we actually see as the dye diffuses.